Hi, I've got a quick tip here to share with you on the use of thermal pads in high ambient temperature power supply designs and why it's important to consider the enclosure design at the beginning of the design process. So what I have here is an RD919 board using InnoSwitch 3AQ. It has a specification of 50 to 1000 volts input and on the output 24 volts and 60 watts. So this is mounted to a cast aluminum enclosure. This kind of enclosure simulates the typical enclosure for an automotive subsystem, say like a traction inverter. So I've added to this 3 temperature sensors. I have one that's monitoring the internal ambient. I have another that is monitoring the case surface temperature. And finally the third is thermally glued to the source tab of the InnoSwitch device. And then over here, this ugly bunch of resistors here is a 10 watt load that's designed to simulate the dissipation of the automotive system inside the enclosure itself, and that causes self-heating of the internal air ambient temperature. So what I'm going to do now is close this up, power it up, and then on the chart recorder we'll monitor the device temperatures. Now when they've stabilized, what I'm going to do is place the thermal pad underneath the source area of the InnoSwitch device and then let it stabilize again, and then we'll come back and analyze the results. So let me seal up the box, hopefully not disconnecting anything. I'm going to turn on the supply and the load. And I've got 2 amps here on the load. I've got 300 volts in, which is kind of the low end of the normal operating range for this supply. So with 2 amps at 24 volts out, plus the ½ an amp inside, I've got a total load on this of 60 watts, which is the rating of the board. So all I have to do now is start the chart recorder. Okay, and that's going, and we'll let this stabilize, and then I'll switch and put the thermal pad in. So I'm going to put the thermal pad underneath the source area on the printed circuit board, and then close the box, and we'll power it up and run the chart recorder again. So I'm now going to take out the pink higher resistance or lower thermal conductivity, to be more accurate, pad, and replace it with the more expensive higher thermal conductivity thermal pad. And it goes right under the source area of the device. There we go. Put the lid back on and then power it up and wait for it to stabilize. Okay, we're back. It's been about 2 hours for this experiment to run, but first let me turn off this noisy equipment. I'll wait for the fan to turn off. Perfect. So what we have on the chart recorder here are the 3 different test conditions that we ran. We have no thermal pad, we have the lower conductivity thermal pad, also lower cost, and then we have the higher conductivity, higher cost thermal pad. If I look at the case where there was no thermal pad, the InnoSwitch, which is the green trace, reached about 60 degrees C. The internal ambient to that condition was maybe 46, just a little bit above 45 degrees C, and the case external temperature was 37. Now what's really interesting, and what the purpose of this demonstration, this tip was intended to show, is when you add the thermal pad, you get a significant drop in the device temperature. So adding a thermal pad under the source printed circuit board area couples the heat that's being dissipated by the device into the enclosure, and it's less coupled to the internal ambient temperature, which is why there's such a significant drop. And by significant, it's gone from 60 degrees C to 46 degrees C. So about almost a 15 degrees C drop. The reason for showing the 2 different thermal pads is to basically save money. The difference between the conductivity on these 2 thermal pads is a factor of 7. So the second pad has 7 times higher conductivity than the first. Yet the device temperature only dropped by 1 degree C. So really it's not worth spending the extra money for a much higher conductivity pad. So I hope I've demonstrated one of the tricks to coping with very high internal ambient temperatures when you have an external case that is at a lower temperature than the internal ambient that the actual power supply is operating in. There was one thing I mentioned at the beginning, which was it's important to consider the case and the enclosure design at the beginning of the design process. But in order to explain why, I'm going to jump to my tablet here and just go through a drawing to explain. So what I have here is a representation of a sealed metal enclosure where the outside temperature and therefore the case wall temperature of the enclosure is 65 degrees C. And in this case, I'm saying the self-heating of the electronics inside the enclosure has raised the internal ambient to 105. And this is the kind of situation where we want to try and reduce the device temperature by coupling the heat from the source area, which is used for heat sinking, to the enclosure. And to do that, and why it's important to consider this at the beginning of the design, is to add a feature to the enclosure, a boss that is grown out of the bottom of the enclosure that allows you to reduce the height between the printed circuit board and the enclosure so you can use the thinnest possible thermal pad. Typically, the minimum is limited by the spacing required for isolation between essentially the high voltage source area and the chassis connected low voltage area. So by doing that, you can either grow a boss, but over here I'm also showing you can shape the enclosure itself to cover other dissipating components on the power supply. In this case, I'm showing it will be applicable also for the synchronous rectification MOSFET or the diode. So by doing this, we can basically heat sink the device to the enclosure and still meet the high operating internal ambient temperature of this particular system. In this case, I'm imagining it as a traction inverter. So one question is, well, why not put the thermal pad directly on the inner switch? And I often see this approach taken, but for the inner switch device, it's actually a power package, and the heat is transferred very effectively from the internal MOSFETs to the source tab. So it's actually less effective to try and heat sink the package through the body of the IC than it is to put a thermal pad on the source area of the printed circuit board itself. There's one other downside to putting a thermal pad on the IC, is that pad now becomes part of the reinforced isolation system. So it has to be, its CTI and its thickness and so on, and the creepage distances all have to be respected when you add that thermal pad. So it just adds additional complication, especially because the CTI of the package is so high. The thermal pads usually have to be oversized because their CTI rating is lower. So we've seen that thermal pads are very effective at lowering the device temperature, and that the enclosure should be designed with a provision to enable a thermal pad to be added if it's needed. We've also seen that the thermal pad specification in terms of thermal resistance is not so critical. And then finally, that the thermal pad should be placed between the board and the enclosure and not the body of the IC in the enclosure. There's a ton more information about this setup and the data associated with it on the website. And if you'd like to take a look at that or any of the other videos, please visit power.com.